So now we talk about how large is the magnetic field inside the solenoid. So still we will use the Ampere's law to derive this stuff. So different from before, we define the Ampere's loop to be a rectangle, or rectangular shape. So half of this rectangle is inside the solenoid, and half of it is out of this solenoid, and of course parallel to the central axis. Well, here we need to make some approximation. We will assume all the magnetic field inside the solenoid to be uniform. Of course, it is not actually uniform. As much as this is close to the wire, then it will not be uniform anymore. And actually, even at this area, it is not perfectly uniform. But we still make this assumption. And other assumption we make is that we assume the magnetic field outside the solenoid to be zero. Although it is actually a small value. It is only a small value, but not actually zero. But here we assume that there is no magnetic field outside the solenoid. Otherwise, we have no way to calculate this value. So it is just an approximation, not necessarily very accurate, but it is good enough. So in this case, we apply the Ampere's law. So on the left side, we have this line integral for this rectangle A, B, C, D. So we need to go from A to B to C to D and then go back to A. So the width of this rectangle is H, and then the height is not really important here. So this line integral can be separated into 4 parts because there is 4 sides. So we integrate from A to B, and then from B to C, from C to D, and then from D to A, and then we add all these 4 terms together. So so let's consider the final 3 terms first. So for CD, we already assume that the magnetic field is 0 outside the solenoid. So for CD, from C to D, it should be 0. For CD, it should be 0. And for BC and DA, BC is here to here, and then DA is here to here. So actually, you can see that DA is perpendicular to the B field inside the solenoid, and if it is outside, the B field should be 0 already. So even inside the solenoid, the loop DS is perpendicular to the B field, which means that B dot DS equals 0 for this one and this one. So the integration should also be 0. So all these 3 terms should be 0. So we have 0 for this part, 0 for this part, 0 for this part. And the only remaining part is AB. Is what we concern, because we concern the B field inside the solenoid. So we assume the B field is uniform. So, and it is parallel to the central axis, and also the loop is parallel to the central axis. In this case, B dot ds is nothing but B times this length, which is H. So we have this line integral to be BH. Okay, so on the left side we have BH. Equals mu 0, I enclosed. So now we will need to consider the I enclosed. So here, this is a cross section of the solenoid. So on the upper row, so we have all the current going out of the page, And on the lower row, we see all the current going into the page. So inside this ambient loop, we can see many current going out of the page. And actually this loop is counterclockwise, so all these current are positive. So actually, if the current of this solenoid is I, of this current of this solenoid is I, we totally have n of the I. This is the I enclosed, and of course it will becomes B equals mu 0 times I times n over h. N is the total number inside this ampere loop, and then h is the total length of this ampere loop, which means that we will define this n over h to be small n, which is the number of turns per unit length. So n is the number of turns per unit length. So it finally becomes B equals mu 0 in. So this is the approximate value for the B field inside the solenoid. It would be somehow overestimated because CD for this integral, if you consider this way, then you can see the B field should be pointing to the left side, even though it is not very perfectly parallel to this rectangle, but actually you for sure contribute a positive value. So actually for this part it should be a positive value. This one should be a positive value. If you really consider this line integral. Of course, we make this assumption because we don't really know how to calculate it. There is no closed form to make this expression compact enough, so we only make this assumption all the magnetic field is 0 outside the solenoid. But at least we know that this one should be positive and it will contribute something on the left side, which means actually this B will be slightly smaller than this value. Okay, any questions? Okay, so next, so we have not only solenoid but also toroid. So actually the toroid is trying to make a solenoid. We try to connect the two ends, and then we make it like a bracelet. So toroid may be described as a hollow solenoid that has been curved until its two ends meet, forming a sort of a hollow bracelet. For the symmetry, we see that the line of the B form the concentric circle inside the toroid or directly. So now we can consider the cross section of this toroid, and then we try to cut it like this, so that we can see so the current here going into the page, and for the outer loop we can see the current is going out of the page. And yeah, you can use the right hand rule. So you use your forefinger to follow the direction of the current, and then your thumb will point to the direction of the B field. So you only try to use your forefinger in this direction, then your thumb will point to this direction. Yeah, so now we consider a concentric circle of radius small r. So you can see this is the center of the circle, and then we choose a small r, which is between the inner loop and the outer loop. And also we assume the B field inside the toroid to be uniform. Not actually uniform, not uniform in this case. But yeah, so we can see that for the Ampere's law, so line integral of B dot ds equals mu0 I enclosed. So on the left side we have B times 2 pi r. The r is the radius of the Ampere loop, and then we have a mu0 n to be the total winding. So I is the current in the toroid winding, and n is the total number of turns. So you need to distinguish. Usually we will have an n for the total number of turns and small n to be the number of turns per unit length. Number of turns per unit length. So when you consider the Ampere loop to be clockwise, so this loop to be clockwise, which means that the positive direction is into the page. So as you can see, all the enclosed current are into the page. So the total number of turns is n. So we have totally in on the right side for the I enclosed. So in this case, we just divide 2 pi r on both sides. So we have B equals mu0 I capital N over 2 pi r. So it is not actually uniform inside the toroid, uniform magnetic field inside the toroid. So it slightly related to the radius, although usually this part will be usually much stronger than this part. So the variation of the small r will be small, but actually the B field really depends on the small r. So in contrast to the situation for a solenoid, B is not constant. Over the cross section of the toroid. So if it is closer to the inner loop, it will be slightly stronger. Any questions? Okay, so we have a sample problem. So a solenoid has a length L and the inner diameter D. So it carries a current I. So it consists of 5 closed packs layer, each with 850 turns along the length L. What is B at its center? So it is a solenoid. So of course we will use the the equation for the solenoid. And yeah, so it should be B equals mu 0 I small n. And of course, mu 0 is nothing but 4 pi times 10 to minus 7 for the mu 0, and then I is 5.57. So this is I, and then times. Okay, so n should be the number of turn per unit length. Number of turn per unit length. So we totally have 5 pack of 850 turns. So the total number of turns will be 5 times 850. This is the total number of turns. However, we need to consider the number of turns per unit length, and it tells you that the length is 1.23 meter. So we need to divide it by 1.23. So finally, the magnetic field should be 2.42 times 10 to the minus second power Tesla. Any questions? Okay, so next we consider a current carrying coil as a magnetic dipole. So of course you know what is a magnetic dipole and also the electric dipole. So as long as they also call it dipole, so they are also called dipole, which means that they will share some similar equation. They will share some similar equation. So here, actually, you can consider a magnetic bar. It will generate the magnetic field lines like this. If you really remove this magnetic bar and then you replace it by a wire with current going like counterclockwise, then it will generate exactly the same. It will generate exactly the same magnetic field lines, which means that actually this magnetic bar and this current carrying loop is equivalent to each other in terms of the magnetic field. They will actually generate the same magnetic field in the space. So we can call the magnetic bar is a magnetic dipole. This loop is also magnetic dipole. So yesterday we already come up with the mu. The mu will be NIA, or if you write it in the vector form, it is like this. So this is the current direction. So mu will pointing upward. Using the right hand rule, you use your forefinger follow the current direction, and then your thumb will point to the mu direction and as well as the A direction. So this is the dipole. So the magnetic field produced by a current carrying coil, which has a magnetic dipole at point P located at distance Z along the coil, perpendicular to the central axis, is parallel to the axis given by this expression. So if you still remember, actually we have derived the electric field for the electric dipole. If we have an electric dipole here, then we can also calculate the E field at this point on the z-axis. So similarly, now we have the magnetic dipole, maybe a current carrying coil or a magnetic bar. Then we can also calculate the B field on the z-axis. So it will be like this. If you still remember, or if you don't remember, I have this one. So now we have if we have a dipole here, then the E field at this point will be this expression. 1 over 4 pi epsilon naught 2p. P is the dipole moment over z cube. Z is the distance from the point to the center of the dipole. So now we have actually, maybe you can just put it like mu 0 over 4 pi times 2 mu over z cube. So now we have a 2p here, we have 2 mu here, we have c cube, we have 4 pi, we have mu 0 on the top, we have epsilon naught at the bottom. So as I mentioned before, usually the equation with epsilon naught, and then for the same set of equation for the magnetic field, you will replace epsilon naught by 1 over mu naught, then mu naught go to here. So actually, you can regard these two are actually the same. So one is for the E field for the magnetic for the electric dipole. This is the magnetic field for the magnetic dipole. Okay, so now we will. Actually we will try to derive this one, but before that, let me try to explain a little bit more. So a current carrying coil, so we have two ways in which we can regard a current carrying coil as a magnetic dipole. So one way I just mentioned is that they will actually generate the same magnetic field in the space if you just set the current correctly, because actually this mu is NIA. So N is the number of turns. You can put more turns so that the magnetic dipole moment will be larger, or actually you can just change the current to be larger or smaller. Then you can tune the magnitude of the dipole moment, or you can change the area of this loop. You make it smaller loop, then the magnetic dipole is smaller. If the loop is larger, then the dipole moment will be larger. So this is one point, and the other one is we have two ways. So it experiences a torque when we place it in an external magnetic field, which means that if we place the loop here, then there will be a torque, and then it will rotate. And actually, if you place a magnetic bar here, you also rotate. So they will share the same behavior under the same situation. So it generates its own intrinsic magnetic field given for distance point along its axis. So this is this case. So it's experiences torque when we place it in an external magnetic field. This is another case. This is from the torque or the force point of view. So this is for the magnetic field point of view. They are the same. So now we try to derive this equation using the Biot-Savart law. Of course, this is a loop. But in this graph, we show it in the cross section. So you can only see something like a line here, but actually this is a circle, this is a loop. And we consider for this point the current is going out of the page, and at this point the current is going into the page, So we apply the Biot-Savart law, dB, so you can get this expression, and we integrate it over the whole circle like this, so we get the overall B at this point. Okay, so So before we do the integration, we know that dB is this expression, mu0 over 4 pi I times ds cross r hat over r squared. First, we consider the direction of the dB. So now we have ds at this point going out of the page, ds going out of the page, and then r should be from this point to the point P to point P. So r hat is in this direction. R hat in this direction, and then ds pointing out of the page, and then what we want to find the direction of dB should be ds cross r hat, ds cross r hat. So ds, you use a forefinger point to ds and then cross to r hat, then dB will be point to this direction, the top left direction. Okay, so this is dB, and then we can actually decompose it along the z-axis, and then also along the xy plane, So dB parallel is the component parallel to the z-axis, and dB perpendicular is the component perpendicular to the z-axis. And actually, you can imagine that for this one is a ds prime. ds prime is into the page, and yeah, for this point, the r hat is pointing this way. So you use your forefinger pointing into the page and cross to r hat, so you will have dB prime points to this direction. dB prime points to this direction. So you can imagine that you decompose this dB prime along the z-axis and perpendicular to the z-axis. So dB perpendicular will be cancelled, and dB parallel will be added together, will be superimposed. So finally, we only consider the dB parallel rather than the dB perpendicular, as B perpendicular cancels. So we only consider dB parallel, and of course mu0 4 pi, we just keep it here, I, we just keep it here. So when we consider the cross product, we need to consider the angle between them, So so the angle between them will be alpha. Not the angle between them. Actually, the angle between them will be 90 degrees. Actually, ds is perpendicular to r hat. And when we need to decompose it, dB into the z-axis, this is alpha, and this is alpha. And of course, dB parallel over dB will be cosine alpha, and this is cosine alpha. So so ds cross r will have a magnitude to be 1 times ds. So we only have ds here. R squared here. And then of course, this component, we need to multiply it by cosine alpha. And cosine alpha, this is cosine alpha. This is also cosine alpha. So for this figure, cosine alpha is cosine alpha is capital R over small r. And of course, the variable we are using is z. So we will try to eliminate small r. So it will be r over square root of z squared plus r squared, like this. Yeah, actually, we've written it here. And r is, of course, r squared plus z squared. Take the square root by the Pythagorean theorem. So we can plug in these two into this expression. We can plug in these two into this expression so that we have dB parallel to be mu 0 I over 4 pi, and then times r ds. So we have r ds. And then over r squared will be only the inside term, and then multiplied by an additional square root of this term. So we totally have a capital R squared plus z squared to the 3 over 2 power. Okay, so this is dB parallel, and finally we can start to calculate the overall B at this point. Of course, pointing upward. Okay, so we plug in this term into here. So actually, this is nothing but a constant. This is nothing but a constant related to ds. Actually, by symmetric, it is, yeah, all of them are symmetric. So you just integrate the constant. This is a constant multiplied by this integral. This integral is 2 pi capital R. So this one, integration of ds is nothing but 2 pi R. So this 2 pi and this 2 pi will be and this 4 pi will be partly cancelled. So we only have 2 here, and then mu 0 I, and then we still have an R here. So we have totally R squared over this term. So this is the exact expression for the magnetic field at this point P. Of course, we can assume that if it is far away, which means that this distance is much larger than the radius of the dipole, of the magnetic dipole. So we assume Z is much larger than capital R, which means that Z squared plus R squared will be approximately Z squared. We can just discard this one because Z is much larger than capital R. So we just discard this one. So C squared to the 3 over 2 power, which is, so 2 and 2 will be cancelled. We only have C cubed here. And then, of course, R squared is still there. So we multiply pi on the top and on the bottom so that they will cancel. But here, what we want to get is, here we have pi r squared, which is the area of the dipole moment. So we form the area. This is the area of the dipole. Area of the dipole. So we have A here. So IA is the dipole moment. Or if you have an n turn, then it's just multiplied by an additional n. So IA is also the magnetic dipole moment if there is only one turn. If there are n turns, then of course it will be n times IA. And still we can make this one to be mu, which is the dipole moment. So you need to distinguish this. Mu naught is the permittivity constant. 4 pi times 10 to minus 7. And this is the magnetic dipole moment. Although they share the same, they share the same symbol, the Greek letters, but with this subscript, then it means the permittivity constant. Without the subscript, it means the magnetic dipole moment. So we use the Biot-Savart law to derive the magnetic field generated by the magnetic dipole moment, and of course it is pointing upward, which means that this is the dipole moment, and then the B field is pointing upward here. So so it actually follows the right hand rule. So you use your forefinger, follow the direction of the current, and then your thumb will point to the direction of the B field. Any questions? Okay, so we have an additional example. So here we can see two circular arcs have a radii A and B, subtend angle theta equals 74 degrees. So this is a 74 degrees, this theta. Carry current I to be a 0.411A. So this is like clockwise current, and share the same center of the curvature P. So the radius of this part is small b, so this part is small a, and these two arcs share the same center. So what are the magnitude and direction into or out of the page of the net magnetic field at P? We want to evaluate the B field at this point. Okay, so now we consider so we consider the simple part first. So for this straight line, it is collinear with this point P, which means that for this segment, it will not generate any B field at this point P. And likewise, for this point, P is actually on the extension line for this segment. So this segment will not generate B field at point P either. So the only part will generate is this part and that part. This part and that part. So when you consider this part, the shorter path with a radius B, so you use the right hand rule, you can see that for this part, it will generate B field pointing out of the page. For this part, you use a forefinger, follow this current direction, and then your thumb will pointing out of the page. And conversely, and for this part, if you use a forefinger, follow the direction of the current, then your thumb will pointing into the page. So that actually, for these two parts, they generate the B field in opposite direction, although the magnitude are different. So in this case, you can see that B will be, actually we will use the equation mu0 I theta over 4 pi b, if you still remember this equation. And this is one part. This part is out of the page, and the other part is into the page, which is mu0 I theta over 4 pi a. This is out of the page. This is into the page. So they should They should be subtract rather than adding together. So we will have mu 0 I theta over 4 pi and then 1 over b minus 1 over a. So we can plug in all the value. Mu 0 over 4 pi is a 10 to the minus 7th power and then times. I will be 0411 and then times 74 degree. We should convert it to radians. So it becomes 47.0 degree over 180 degree times pi. And then we have a 1 over b, which is 1 over 0.107 minus 1 over 0.135. So it turns out to be 1.02 times 10 to minus 7 Tesla. So this is the magnetic field generated by this loop at point P. And actually, I'll also ask you the direction, and the direction should be out of the page, because this part generating the B field out of the page, this part generating the B field into the page. However, this one is larger. This one is larger. So this is out of the page.